So it won't go anywhere down. Like I can control it.
Okay, now same model.
Tire will just like go, I can control it.
We've got the y-axis. We've got the x-axis.
I do that.
And we've got densely packed sources along the y-axis. I'm not drawing a really dense set, and I'm kind of talking about the topological meaning of dense, and you don't know that definition, but let's not worry about it. You got a whole bunch of these within any many sources within any segment of length lambda. Okay? Now what's going to happen when you put these sources, when you start driving these sources, and again we're driving them in phase, I'll actually state that one this time, in phase, is, well, you're going to get a wave front that comes out. Okay, the first wave front is going to come out. I'm only going to draw this on this side, but of course, since this is, a large membrane, and the same thing will happen on the other side, right?
Right.
So things will, spread out in both directions. Okay, so the first source is going to do this, right? Okay, so I'm not going to draw them all. Or the first, or let's say the most recent cycle will give you a peak here on this circle at uniform distance from the source. Remember, these things travel the same speed in all directions, okay? If you have a different speed in this direction than this direction, you get little ellipses. Think about that, but that's just a side comment. Okay, well, the source before that is going to be where? Going to be here. Right? Okay? And the one before that one is going to be here. Okay? So, what do you have? Let's say this thing's been going on for a long time. What happens out here at distance B at time at time t equals b over c from the time the disturbances began. What are you going to see in the plane? Well, at time b over c since the start, the very first peaks are going to get here, right? And there's going to be nothing beyond this. Okay? So you're going to have, you're going to have a peak from here at this point. A peak from here is going to be at this point. A peak from here is going to be at this point, and so forth, right? That make sense? And the next peak is only going to be a little ways behind. Okay? And also the circle is going to have a great big radius here, right? So the circle is going to have like this radius. So if I draw a circle of this radius here, well, that means that you're going to have pretty much this here, and this here, and this here, and this here. Okay? These things are almost flat, aren't they? Now the other thing is I haven't drawn them all. Okay? Yeah. there are 10,000 of them between here and here. Pick an arbitrary number, right? So what's it going to look like here? Well, here, you're basically just going to have one extended peak. Okay? Does that make sense? And in the limit, it's like you're driving this whole thing in simple harmonic motion. So you're just creating waves here that just go out in wave fronts, right? Now, where's the next peak going to be? I mean, you know, the preceding peak is going to, well, the preceding peaks are all going to be along a line like here, right? One wavelength behind this, right? And then we're going to have a series of peaks here, just like waves in the ocean, but it might not be waves of that nature, okay? So we have what we want to call wave fronts. Right? And these wave fronts make planes. Yeah, they're in succeeding planes, right? So we call this a plane wave. Okay? That's what we mean by plane wave.
Like plane, like you fly a plane.
Yeah.
Space plane.
And what's the direction of propagation? In what direction are these planes moving? Perpendicular, right? To the plane, right? Normal to the plane. And I can use the word normal, just means perpendicular to, but we're familiar with that word from other courses. Okay? Now you're probably thinking in terms of mechanical waves, because we started with waves and strings and stuff, but light waves behave the same way, and we're going to do some stuff with both types of waves this week and probably next. Okay? In lab. So there's a model of a plane wave. Okay? Well, it gets even better. Okay? Now actually, this is an x equals b. Now I've obliterated x equals b here, but I'm going to redraw it in a different color. And I'm going to say, okay, this is great, but let's say there's a barrier at this point. Okay? So we're going to have a barrier at x equals b. But you know what? That barrier is going to have two openings in it. So I'm fudging a little bit because this is a little to the right of where I said x equals b is, but you know, you get the idea, and we'll only talk about one wavelength difference. Okay? So those openings are positions B A over 2 and B negative A over 2. Now this ought to start reminding you of what we just saw, right? Okay. Well, what happens? What are you going to see to the right of this?
Nothing? Or,
No, you got an opening here. You got an opening
Oh.
here.
It'll just be,
small, could be,
one portion of the wavelength on,
no, you would like expand.
Okay, yeah. What Nelson is describing is kind of, okay, well, you're going to get, actually, you know, this is going to be in motion with frequency f, right? So is this. So one way to see what you've got is you're going to have, well, you're going to start having expanding circles here, right? And expanding circles here. These are your wave fronts, okay? And we'll expand a couple more because we want to see what this picture looks like, and I'm kind of on a roll with drawing decent semicircles, but now that I'm aware of it, I'll probably screw it up. Okay? Now these are in phase, remember, right? Well, that means that at this point where the little circles intersect, and at this point, and at this point, and at a series of other points, you're going to have positive reinforcement, right? Okay? That makes sense? And the line of positive reinforcement is not actually a straight line until you get a little ways away from this, several wavelengths away, then it becomes a very straight line, okay? And at some angle alpha, with this axis, with the condition that A sine alpha equals lambda. Okay? In other words, what you're going to see here is exactly what you saw before, but with the origin maybe shifted over to here. So there's one circumstance under which you could achieve the thing that we've just been talking about, right? Now we're out of time, but that never stopped me. Let's see. Let me check the time on this. Yeah, we got a minute or two. This won't last more than 3 more minutes because that thing's going to be over time, and that's a real hassle. If I have a bunch of little holes in here, what am I going to get? Well, I'm going to get another plane wave. Okay? But it will have lost energy because this thing's going to lose energy. It's going to reflect when it hits here. Okay? And that's actually of interest too. You know, you're going to have reflection. These are going to reflect back. Okay? So at least near this point, you're going to have points where the reflected waves reinforce the incoming waves and points where they cancel. Okay? So you're going to have places where you really don't want to be if you're in a small boat, if this is water, and places where things are relatively calm. Okay? So all those things are worth thinking about, and they all start just from the idea of a number of little sources. And Huygens' principle is just basically the principle that every point on a wavefront acts as a source for all future points.
So if you were in water, you'd want to be along that line, wouldn't you?
If what now?
If you were in a boat, you'd want to be riding along that line, right?
No, you'd get beat to death against the breakwater.
Breakwater? Okay.
If this is a breakwater,
Uh-huh.
you know, like in Lake Erie, you know, fairly shallow lake, so, you know, a couple hundred yards out from shore, they just built up a big old pile of rocks about 60 feet high. Okay? And it's, you know, like 40, well, it's not that, water's not that deep out there. Whereas maybe 20 feet deep out there. So they built a 30-foot pile of rocks to keep the big waves, which are just as big as ocean waves, because of Lake Erie shallowness and winds and stuff, from eroding the shore. And also to protect people who might be swimming inside the breakwater or boating inside the breakwater. It's a big deal if you take your boat outside the breakwater on a windy day.